It's just 3 videos for this chapter. I wasn't kidding when I said it was a shorter chapter. And this one will probably be the shortest of the 3 videos. So alloys are just what happened when you mix different metals. So there's, the metal titanium. People wanted to make stuff out of titanium. It was a nice strong metal. It was lightweight, but it was very brittle. So there were some issues with being able to work with it. Well, they figured out how to make alloys and leverage the strengths of titanium and mitigate its weaknesses. So for a lot of different types of material design, you can use titanium alloys to design something that would be a little bit stronger than if it was made out of steel. It's kind of an upgrade on steel. Now we've gotten better at working with aluminum, so that's even lighter. A lot of times now they're going to aluminum construction. But it's not as strong as titanium. So if you really need something strong, you go with the titanium alloy. But what it does is we have something different than the pure metal because we've mixed in some other metals. So like steel is an alloy. It's different than iron. It's an iron alloy, but it has very different properties. And so we introduce these new atoms with different sizes. It changes our unit cells, changes our stacking structure. The pieces kind of shift together differently, and that gives us new properties. And there's kind of 2 types of alloys. And so you can have something that's like a pure metal, like you can have pure iron, and you can have something like an interstitial alloy. And what that means is that we have these new atoms and they fit in the gaps, they fit in the spaces between the metal atoms that were already there. So that's one option. You have these smaller interstitial pieces. Or there's a substitutional alloy, and that tends to happen when the new atoms are about the same size as the old metal atoms. And so what happens is they replace them in the structure. And both of these create, new stacking structures with new properties. They just do it differently. Like again, it's seeking kind of an efficient packing process. And so if there's space to fit something small, they do. And if there isn't, they don't. It's as simple as that. And you can do both. And so there's a ton of different types of steels out there. Carbon is something they put in a steel. Nitrogen. They can sneak in some other metals as well. And so you can get, substitutional alloys, you can get interstitial alloys, or you can create a situation where you put all kinds of stuff in and you get both. And so you get a substitutional and interstitial alloy. And so this is called interstitial because it goes, this is like the interstitial space, in between the atoms. This substitutes for an atom entirely, so it's substitutional. That's where the names come from. And mainly just, understand the difference in how these pieces are coming into play. Are they replacing a pure metal atom, or are they fitting in the gap in the middle there? That's really it. And how do you know if it's going to fit in the gap? Well, if it's small. You got something small coming in, boom, it's going to fit in the gap. If you got something large, it's going to have to, take the place of a whole atom because it's not going to fit in this space right here. This is too large. All right. And then the last thing. So this is all just mixtures of metals. Sometimes nonmetals get worked in alloys, like I mentioned with the steel. But plastics and polymers, these are a very big part of our everyday life now. Like plastics are a material. My computer's made out of plastic. The mouse I'm mousing around with is made out of plastic. My keyboard, and our lives would be very different without it. And so these can be an amorphous solid or a glass. Most polymers tend to be an amorphous solid. Occasionally they stay in the glass phase. They all have a glass phase that's accessible to them. When you're working with polymers and you heat them up and cool them down, they tend to transition through a glass phase. Like I mentioned in a previous video, it was polymer research groups, or it was a polymer research group that identified glass as its own phase. So it wasn't like a type of solid, it wasn't a type of liquid, it was a phase. It has solid properties, but it has liquid properties, and it has its own unique thermodynamic properties as well. And so it was polymer research that really made that point, made that discovery. And so these are going to be really long chains of carbon compounds. Like they're going to be incredibly long. So they're like these really long, kind of, you can think of as molecular spaghetti noodles. They are flexible individually, and so what happens is they wrap around each other, they get entangled with each other. It's like, they're becoming less popular now, but headphone cords. There's a reason people like cordless headphones, and that's because your headphone cables did a great job of displaying the property of entanglement. They get tangled up with each other, and you'd spend 5 minutes trying to get a knot out of it or something. And that's something that helps hold these things as solids. It plays on these London dispersion forces and helps it hold together. So they are typically non-polar compounds, but they are so massive with so much surface area that they have a ton of dispersion forces. Plus the fact that they can literally tie knots around each other and become entangled helps hold them as a solid. And so different polymers, depending on what we make our polymer out of, call it a monomer. So right here, this would be ethylene, would be our monomer. And then we can polymerize it into polyethylene. And so this N value can be hundreds to thousands to hundreds of thousands of middle pieces long. So this is just a chain that just runs and runs and runs. And we put a bunch of them together. We melt them together, we cool them down. And so this would be a plastic that would be used in something like plastic milk jugs. If you buy like a gallon of milk, or sometimes half gallon comes in plastic, or juice, things like that. Very non-reactive, very stable. But it'll have very different properties from something like styrofoam, which is also known as polystyrene. You don't make plastic milk jugs out of polystyrene because it's more brittle, but you don't use polyethylene to dispense hot drinks because it doesn't insulate very well. It's going to conduct the heat a little bit better. Polystyrene, the old styrofoam coffee cups are popular because they help keep your coffee hot. Sorry, not cold. Help keep your coffee hot. And also it's very lightweight. But you can also prepare polystyrene. You can prepare it in a way where it is less insulating and more rigid um, by kind of melting it back down and solidifying it, things like that. So you can't do that process with polyethylene though, where you kind of make it fluffy and insulating. It wouldn't be strong enough. But styrofoam, you could do that. And so really, it's just you know what a plastic is. You're not going to have to like diagram one of these reactions. That's an organic chemistry thing, but just kind of understand what holds plastics together as solids, and just the fact that there is no real universal property for them. That's what makes them so important in today's lifestyles, is because we can tailor a polymer to whatever need we have. And so for a long time, it was making plastics that lasted for as long as possible. The original plastics were not very durable. They would break down over time. So in the 60s, you started to see plastics hit the market. Like the original Barbie dolls are kind of decomposing because they were made out of those original plastics. So they have to be stored very carefully. Like they literally will the plastic just falls apart. And so what we spent decades doing was mitigating that in the plastics. And now you can have a situation where a milk jug gets left in a desert for 20 years and all it looks is a little sun bleached. That's it. It hasn't broken down. And that has become an issue because now the ocean is filling with these, what we call immortal plastics. And so now these polymer researchers have shifted gears again. It's like, okay, well, we can make a plastic for anything that we could ever imagine. We can make it last longer than I'm going to be alive. So what's the next step? Well, now we need to make it so that they're more easily recyclable, that they're biodegradable, that they don't last forever. Let's try to actually nail a lifetime on these plastics. Let's make them last. You don't need a milk jug that's going to work forever because it's not like you're using the same milk jug over and over again. What do? You recycle it. And so making it so that these single-use plastics can be more environmentally responsible. That is really where plastic research has gone. The other direction that it has gone is what we make the plastics out of. So something like ethylene here, this is going to be coming from an oil refinery. This is going to come from an oil well. There's no good natural source of ethylene, like not in our feedstock chemicals right now. I'm not saying it can't happen, but typically what you're going to do is you're going to buy a thing of ethylene, and it's going to come from some oil refinery somewhere, some chemical plant. All right, so essentially it came from the ground. But what they're looking at now are, there's like the cafeteria had some cellulose corn starch-based plastics that were made from renewable resources. So this ethylene right here would not be considered a renewable resource unless we came up with a renewable way to produce ethylene. And that's the other direction plastics have gone, is they've gone to the end product, making that more responsible, but also looking at what we start with and being a little bit more environmentally conscious there as well. And there have been breakthroughs in those directions, but it is more expensive still. And so you don't see a complete wide adoption of that. And so this is an issue that we're going to have to face down over the next generation or so and figure out how we're going to manage plastics responsibly, because otherwise they all just end up circling in an area the size of Texas in the Pacific Ocean apparently. And as far as I know, no country is really interested in cleaning that up. There's been individuals that have done some stuff, but it is such a massive undertaking that ideally what we could do is create plastics that don't end up capable of doing that. They break down in the ocean, they break down when they're buried in the ground, so on and so forth. So we don't have these immortal plastics. And there is only so much oil in the ground. So what are we going to do when that starts to become scarce? What are we going to make these out of? Because we have become so reliant. I mean, this is not just a convenience, but for many situations, it's a life-saving technology. The incubators for premature babies are made out of plastic, and that was a huge breakthrough there. The ventilators that are being, produced all over the country heavily employ plastic as well. So this is a very important life-saving technology. And keeping it going as the feedstock chemicals start to become scarce is a very important issue as well. And so that's where they really focused. All right, but in general for this class, just understand the basic idea of these plastics, and that's it. I'm not looking for a ton. Like this is, you could spend an entire career researching this stuff. You can spend an entire year of chemistry courses on it. Like it's a big deal. And same with things like alloys and all of these solids. Like this is all inorganic chemistry. The way they put these together, it isn't always, there's the old-fashioned way of you just mix metals and you cool them down and you see what you get. And there's the newer techniques too, where they like layer it on glass and they get all these interesting compounds where they can really tailor make processes, and they can do vapor deposition and produce new semiconductors and things like that. So there's a ton of detail here that we're not going into. It's one of those chapters where some of the stuff's just too crazy to talk about in Gen Chem, and the rest of it's pretty basic, like the idea of a solid. So, like I said, I cut this chapter test down. It'll be about 12 questions. It'll be worth 25 points. So, this is kind of like a easy week. I'll admit that. This is an easy week, but prepare, get ready, because chapters 13 and 14 are going to take it to you. So, there's going to be a lot more math in play in the next two chapters. There's going to be some very important ideas because we are going to look at a whole new perspective on chemical reactions over the next two chapters. And then chapter 14 is going to be vital to your start of 223 if you're taking that course, because it's going to carry right into the next two chapters of that course, or the first two chapters of that course. So enjoy this week, but get ready. That's my advice.